right, welcome to mini lesson 21. This is the last new material for spring 2020 of Physics 413. So what we're going to talk about is the thermodynamics of non-ideal mixtures. In the last lesson we talked about ideal mixtures, where the components of the mixture had no interactions and that the only effect of mixing was the entropy of mixing. And that's a really important factor, but taken by itself is actually not very realistic at all. I mean, unlike the case of ideal gases where it's actually quite common to have gases in the world that are approximately ideal, it's, I think, much more rare to have mixtures that are ideal in the sense that we talked about last time. So we're still in section 5.4 of Schroeder. And so just to remind you of the result of discussing ideal mixtures and the entropy of mixing is that we can calculate the free energy of a mixture, and we can compare two curves for any composition of the mixture where composition is defined by the fraction of one or the other of the components, because once you know the fraction of one, you know that of the other. So in an unmixed state, the free energy is just a linear function of the composition. In a mixed state, the linear function is corrected by subtracting off T times the entropy of mixing. And so you get a curve that's at every point lower free energy than the unmixed state, and that's the red curve here. So the weird bowing curvature comes from the fact that the entropy of mixing has these logarithmic terms in x sub b. And so the idea here is that in a real mixture, we'll need to add more physics than just the entropy of mixing to understand the true free energy of the mixture. But the analysis that's probably most important here in all cases is graphical analysis. On a G versus x sub b plot, to find out at any given value of x sub b what state of the system will be achieved, you're just going to be looking for what curve at that point has the lowest free energy, right? And so the reason this topic is so valuable in an introductory course on thermo and stat mech is that the analysis that we do here is to basically think about a competition between entropy effects, in this case entropy of mixing, and energy effects, which we're going to add on now. And this competition is really important to think about in many, many different contexts beyond mixing. But I think mixing gives you a very clear background in how to work through that competition when you would need to apply it even to other systems. So really valuable application in my opinion. So let's look at non-ideal mixtures and what we mean when we're going to add new physics other than just mixing. And so the basic idea is that let's say we start with an unmixed state and there are numerous interactions in each of the phase domains, right? So this is where x sub a, the blue boxes are called A, right? So this is all A. And inside this domain A, there are lots of favorable energetic interactions between A molecules and other A molecules, okay? So if you want, you can think of these as just sort of the van der Waals type dispersion interactions between any molecules. If it was water, say, it would be hydrogen bonding between water molecules. So then the idea is that if we made a mixture, we would be creating a lot of circumstances where instead of having an A to A interaction, you would replace it with an A to B interaction. And the assertion is that in many, many cases, this interaction between A and B is less favorable than between A and A. So we start with an energy, a potential energy of interaction between A and A, which is U sub AA here. We replace it with U sub AB, and we claim that U sub AB is less favorable. In other words, it would take an energy input to change this into this, right? And so it looks like mixing has a net unfavorable contribution to the free energy. In other words, you would have to take energy from the environment in the form of heat to cause the mixing to occur, because you would have to disrupt this interaction and replace it with a less favorable interaction, AB. And so the energy as heat that you would need to do that is just U sub AA minus U sub AB, and that would be the value of the energy that would need to be transferred into the system to create the mixed state from the unmixed state, right? And so the important point is that that energy transfer will lower the entropy of the environment. If you extract heat from the environment, you're lowering the entropy of the environment. And if that effect is bigger than the entropy increase of the system due to the entropy of mixing, mixing might be net unfavorable, right? It might lead to a net decrease in entropy of the whole universe, even though it's always increasing the entropy of the system. So I guess we should say this doesn't have to always be the case, but this case that we're sketching out in these cartoons is common enough that it's the one we need to analyze. So if you had an opposite case where the interaction between AB was more favorable than the interaction between AA, in that case, it's almost like an ideal mixture, right? Because mixing is then always going to be guaranteed to minimize the free energy no matter what happens. So it's not really worth thinking about in detail the opposite case where this picture that we're sketching on this slide is not true. But again, this is actually the most common situation you'll find for most mixtures, and so this is really the one we have to pay attention to. Okay. So what we want to do is make a specific model of how to deal with that unfavorable energetic effect of breaking the AA bonds or AA interactions, they don't have to be bonds, and replacing them with AB interactions, right? And so we want to basically come up with an idea of what specifically should we say about the more physics that we want to add to the free energy of the mixture in the ideal case, right? So let's see what has to be true about the more physics. We need to add a positive term, right? Because we're doing something that's unfavorable. It should increase the energy of the free energy of the system. It obviously has to have units of energy because we're going to add it on here. And it needs to depend on the fractions of materials, and in fact it needs to depend kind of on both of them in some way, right? Because we're sort of talking about, are there AB interactions as compared to AA interactions? And so the simplest proposal that has been made for a model of non-ideal mixture effects looks like this. You write a potential energy term U sub 0, which is a constant energy value that sets sort of the energy scale of the unfavorability of the interaction. So this would be a material dependent parameter. And then it needs to depend on the fraction of A molecules that are present. And it also needs to depend on the fraction of B molecules that are present. And we do that as a product because what we're really talking about here is like a probability that an A and a B are next to each other in the system. And so probability that an A is at some point is probably proportional to X sub A. And the probability of B is proportional to X sub B. And if we're thinking about probabilities, when we use the word and, our fundamental principle of counting tells us we should multiply. So this is a model, right? What I just, there's no rigorous mathematical derivation of this model, but indeed this model satisfies all of the criteria that we need physically, right? So as physicists, we're making a model that's based on sort of ideas about how the physical world should work, and not about what math must always be true. So this is a reasonable form. Let's see. So we want to write the expression here that we've guessed in terms only of x sub b, because xa and x sub b are not independent. So we just substitute in x sub a is 1 minus x sub b. So now we can write out the whole Gibbs free energy for a non-ideal mixture. It's the isolated free energies of the species. Those are those first two terms. T times the entropy of mixing, so that's that complicated logarithm term that we got by doing the two-state multiplicity problem. And then we just tack on this unfavorable energy term, right, that has a scale u sub 0, and it depends on x sub b. Importantly, it depends on x sub b quadratically, right? So whereas the isolated state contributions are linear in x sub b, this unfavorable term is quadratic. All right. So this is a really important formula because this is basically the free energy for a non-ideal mixture. So I probably should have put a box around this. Now let's see how it looks graphically, because I think you get your best intuition about this from analyzing the graphs. It's almost guaranteed that I would give you a graph on an exam. So you should pay a lot of attention to the graphs that you're about to see in these next few slides. So I draw three curves here. I draw, as we always do, the unmixed linear terms in blue. For reference, I put the case of an ideal mixture. It's important that this is just for reference. We're not saying there's a possibility of having an ideal mixture. We're going to only be considering that you could either have an unmixed physical system or a non-ideal mixed physical system. I'm just showing the ideal case to show you that when I add in a term with a u naught corresponding to the unfavorable interaction, I raise up the free energy from the red curve. And at this temperature, about kBt equals 1 electron volt, I raise it up by, not a huge amount, but a noticeable amount. And so the important point is that if I have this interaction strength combined with these other conditions in the model, the unfavorable interactions due to mixing are not enough to cause mixing to become unfavorable, right? So still the green curve is lower than the blue curve, and that means at any composition along this axis, it will always be favorable to mix A and B, right? So another thing you can point out here is that no matter what's happening here, as we let x sub b go to 0 or 1, all the curves are sort of starting to intersect one another, right? And so, under those conditions, you don't have a mixture anymore, so you expect, in other words, all A just looks like A, all B just looks like B. So let's look at graphs like this as we start to change the energy scale of the unfavorable interaction, u sub 0. So all of the plots on this slide are showing different values of u sub 0. Right? So on the last one I did 1 electron volt, and in that case we raised up the free energy curve a little bit, but we fundamentally didn't change the question of is there mixing versus not mixing. Excuse me. So when we increase u sub 0 to 3 electron volts, the situation is very, very different, right? Depending on where we are in x sub b on the x-axis, the lower curve changes, right? So if we're at very small x sub b, less than, say, 0.25, the green curve is still lower than the blue curve, and we would expect mixing. But as we cross this value, which to my eye looks like about 0.25, it starts to be true that the non-ideal mixed curve is higher in free energy than the blue curve. And so, for example, if your mean old boss told you to make a solution where the fraction of B was 0.4, right? You would say, sorry, boss, that's not going to mix because the free energy in the mixed state is higher than the free energy in the unmixed state. And that would be true for any composition between these two dashed lines. We would have no mixing under these conditions. You only have mixing under conditions where the fraction of B is either very small or very large. And as you increase U sub 0, the range of compositions where mixing is unfavorable gets wider and wider. So here at just 3.5, so just a tiny bit bigger, we've pushed the range of compositions where we get mixing down even further to sort of like 0.18 or something like that, and lower, and then symmetrically on the other side. This whole free energy is perfectly symmetric about xb equals 1/2. And so this is not 3.5. This is a typo. This should be 5. So when we increase U sub 0 to 5, this goes farther out to almost 0. And what I did here was to zoom in real close on these ends to find out, is there any composition where mixing is favored for this strong U sub 0 equals 5 interaction strength? And the answer is yes. So it looks like if you're less than about 0.18, you start to have the green curve being lower than the blue curve, right? And so you would tell your boss in this case, okay, the only solution I can make for you is a solution where the fraction of B is less than 0.018. So that's like less than 2% of the B component. It's really interesting. The reason I'm showing this is not just because it's interesting in these special case of these particular values, but it's always true for a mixing problem that you'll be able to find a small enough x sub b value or a large enough x sub b value, because it's symmetric, where mixing will be favored. It might be unbelievably small, right? It might be x sub b equals 10 to the minus 6 if the interaction is really, really strong. But there's always some value where it's true that mixing is favored. And that's actually a really interesting and practical point, because it sort of tells you that if you're making a new material in the lab, the idea that you can have absolute purity in your material is nonsense, right? Because there's always a thermodynamic driving force to have a very small amount of impurities. And so it's really, the thermodynamics of creating a pure material is almost inconceivable in a real lab situation where you do have potential for very small quantities of impurities. They will come in almost guaranteed. All right. So now instead of varying U sub 0, let's go ahead and vary the temperature, because in addition, so the interaction strength U sub 0, you would control in your lab by essentially by changing the material, right? That U sub 0 value is determined by what material did you choose for A and what material did you choose for B. And once you've chosen your materials, you're basically done in our model. So, but another important point, and probably the point that is of most practical value in the lab, is let's say you've got a fixed U sub 0 because you know what materials you need to mix. What temperature, what is the effective temperature on the question of mixing versus not mixing? So over here on the left, we have a very low temperature, T equals 0.1 eV. And in that case, at low temperatures, the blue curve, which is the unmixed state, is always lower than the green curve, except at some really teeny tiny value, like I said before, it will cross over. Right? I didn't plot it here. So basically, for almost all compositions at low temperatures, mixing is not favored. And it's actually really important that this is not a kinetic effect. We're not saying at low temperatures you don't have enough kinetic energy to get intermixed. That's not how we do thermodynamics. That's a kinetics analysis when you talk about, oh, everything's just too slow to mix. In thermodynamics, we imagine that if things are happening slowly, we're going to wait and give them enough time to come to thermal equilibrium. This statement on the left is saying if you would wait for infinite time so that everything has enough time to come to thermal equilibrium, there's still not mixing in the low temperature case. So make sure you pay attention to what I just said. It's a subtle distinction, but such an important one that you really need to pay attention to it and not imagine that it's just some extra that I've added on here. In thermodynamics, we don't think about things happening super slowly. We don't think about time dependence at all. We always give ourselves infinite time to allow things to come to thermal equilibrium. All right. So this middle plot is the same one that I showed you before, where we have a temperature of 1 eV, a U sub naught equals 3 eV, and we have a fairly broad region where mixing is preferred at small x sub b, and also a fairly broad region near the middle where mixing is not preferred, where the green curve is a higher free energy than the blue unmixed curve. And then as we go to really high temperatures, 3 eV, we have a situation where the green curve is always lower than the blue curve. And so at high temperatures, mixing is always preferred. Again, don't mistake this for some sort of kinetic effect where you've given so much energy to the molecules of B that they can just ram themselves into A. That is not the physics here, and you must not confuse yourself by thinking it is the physics. There's no dynamics in this analysis. In other words, there's no dynamics in thermodynamics. What we're saying here is that at high temperatures, the entropy of mixing dominates the free energy of the mixture. And so you can always minimize your free energy by mixing at high temperatures. So let's just take a look now at how we would think about what I just showed you in the last slide in terms of a kind of phase diagram. And so what I'm plotting, this is sort of a typical convention that people use to plot this. We'll plot temperature on the y-axis and x sub b on the x-axis. And so then the question is, for a given combination of temperature and x sub b, would your mixture be unmixed or mixed, right? And so at a temperature of 0.1 from that last slide, we had a very large range inside this volcano-shaped dome where we have an unmixed state, right? And only for very small x sub b's out in this little window here would we have a mixed state at 0.1 eV. Okay, so these blue circles are the symmetrically located points where the blue and green curves cross from the last slide. Okay, so at 1 eV, this region of unmixed becomes quite a bit smaller, and so if we would go to an x sub b in this window, mixing is now favorable. Inside the dome, mixing is unfavorable. And then I did one other calculation where I slightly increased the temperature from 1.0 eV to 1.07 eV. By the way, please don't get upset with me for writing temperatures in terms of electron volts. That's a sort of standard analysis. The reason for doing it is to just make it possible to directly compare the numbers in this list. Anyway, so for t equals 1.07 eV, you have basically the green curve just barely kissing the blue curve, barely coming over, so that you have a really narrow spot where unmixed is equally favorable to mixed, right? If the blue and the green curve touch, it's mixing and phase separation or not mixing are the same free energy, right? So in our model, we're always going to get a phase diagram that sort of looks like this volcano-shaped curve, where under the dome is unmixed, outside of the dome, anywhere in here, is mixed, okay? And so this region under the dome of compositions where mixing is not favorable is often called the miscibility gap. I think I said that on the last slide. No, I didn't. Solubility gap, whatever. I said on the other slide. Yeah, so miscibility or solubility gap is this sort of region, the width of this dome, right? So at low temperatures, it's large, and as you go up in temperature, it shrinks to 0 at this final tippy top point. And so the basic point is at the top of the dome is the composition where you can maintain separation at the highest possible temperature, okay? So this is a nice phase diagram that actually describes the mixing. So before we stop here, again, I want you to really go through and pay attention to what I said about these diagrams and how you would analyze them. The key point is you're always looking for, at any given x, what is the lowest free energy you could achieve, and that will tell you what state the combined system will attain. But let's just mention quickly an application. Sorry. So an application that's really important to me and to a lot of people at NC State is the design of organic solar cells. So organic solar cells are where we use sort of these brightly colored organic dye molecules and polymers to make relatively low cost and relatively environmentally friendly solar cells. And they're really interesting. There's a lot to say about them. Let's not dwell on the details, but there's a special mechanism inside these organic solar cells that requires you to take one of the organic materials as an electron donor and mix it with another type of organic material that's an electron acceptor. Right? And so you just have to do that to make these types of materials turn sunlight into electrical current. Okay? And so the point is, if you're trying to make a solar cell that will actually make a dent in the renewable energy industry, you can't just make any old mixture of electron donor and acceptor. You need to make one that's works really well. And that's what a lot of work that we do in the organic and carbon electronics lab over on Centennial Campus focuses on, is how do you make the best mixtures? What are the best mixtures for organic solar cells, right? And so we're basically taking a donor, which in this case is shown as the green spaghetti, and an acceptor, which is the red balls. And we ask the question, well, what processes can we do to control how these things are mixing? And what's the effect on light absorption? That's important for solar cells. Charge motion, obviously important, because you do need to generate current and get it out of the cell to power devices. You also need to think about the long-term operation stability, right? If you make a mixture that's just barely stable, that's not going to be good because it's not going to last long. And you also need to think about, can you make these mixtures as coatings that can cover super large areas for large solar panels. So I'll just show you one more picture that's related to this. This is an article from the ADE group just last year. Masoud Ghassemi was a graduate student at NC State who's now a postdoc at NC State. And he led this article that appeared in Joule last year, where they talked about delineation of thermodynamic and kinetic factors that control stability in these solar cells. And so the thermodynamic analysis that they did was basically to analyze in great detail these mixing phase diagrams that I just told you about. And so in their notation, what we call X sub B, or what Schroeder calls X sub B, they call phi polymer, but that's basically the fraction of the polymer that's this green spaghetti in the solar cell. And they're basically talking about the various features of this temperature composition mixing diagram. So it's important that the shapes that they show here for their mixing phase diagram are not as symmetric as the ones that we've done in our model. And that's because they're thinking about some more complicated additions to the model. And to put it simply, what they consider is a situation where the interaction energy has exactly the same form as the one I just showed you. So there's an energy scale times x of b times 1 minus x of b. So this expression stays exactly the same. But the thing that they do in the Ade group and many other groups that work on this is that they imagine that the scale parameter, the u sub 0, is actually a function of temperature. So sort of, you know, the unfavorability of the interaction is a function of temperature. And how exactly they get this form is sort of complicated, but it's also not, I mean, it doesn't come from fancy pants math. It actually comes from installing physical intuition into this model. So it's really nothing particularly, like you don't need a special course to understand where they get this. You just need to start to understand the physics of these types of materials. So in any case, this is actually, this mixing problem is really important, and I would say with what you know right now from this course, you would be ready to step into the Ade group and start working on these models. Even though they're slightly more elaborate, right? You've got the background today, so congratulations. All right, so that's going to be it for new material. This discussion of mixing effects will be on the final exam, and I'll have more to say about the final exam later this week. So we'll talk with you later.